Hello students, in my last lecture we talked about various types of electrodes, concentration cells and liquid junction potential. Now today we will talk about applications of liquid junction potentials and potentiometric titration. The first thing is that we use concentration cells all around us, for example, in nerve signaling, that is, concentration gradients produce electrical current. Second, ion pumps across cell membranes, for example, sodium, potassium ions, calcium ions, these are used across cell membranes. Third, energy production and storage in cells, for example, ATP, that is adenosine triphosphate. pH meters, they usually involve concentration cells, or we can say liquid junction potential, and these usually use a silver chloride reference electrode rather than a standard hydrogen electrode. Ion selective electrodes, there are different choice of reference that can be made specific for specific ions. Determination of the valency of ions in doubtful cases can be determined using concentration cells or liquid junction potential. For example, the valency of mercurous ions was in doubt for a considerable time. It was finally established by determining the EMF of a concentration cell of the type given as mercury, mercurous nitrate at concentration C1 separated by double vertical line, mercurous nitrate C2 and mercury. The EMF of the cell E, assuming the activity coefficients to equal to unity, is given by the expression E is equal to 0.0591 by n log C2 by C1, and this relation is valid at 25 degrees Celsius. In this equation, n is the valency of mercurous ion and C2 is greater than C1. It was found that when C2 by C1 was nearly 10, the EMF was 0.0295 volt. Therefore, the valency of mercurous ion is determined as 2. Second application is in determination of mean activity coefficient. When M1 and M2 are the molality and gamma 1, gamma 2 are the respective mean activity coefficient, the EMF of a cell can be expressed as E is equal to RT by F log M2 square gamma 2 square divided by M1 square gamma 1 square, and this is equal to 2 RT by F log M2 gamma 2 divided by M1 gamma 1, as activity of HCl is equal to activity of hydrogen ions and activity of chloride ion is equal to M square gamma square. The equation can be utilized to calculate the mean activity coefficient of HCl. The equation also provides the molalities M1 and M2 and mean activity coefficients at any other molality M1, that is gamma 1, are known. The next application is determination of solubility product. For example, consider a salt Mx in equilibrium with its ion in a saturated solution. So, let us write an equation: Mx solid is in equilibrium with M plus aqueous plus X minus aqueous. The solubility product of the solution is given by an expression Ksp is equal to Am plus multiplied by Ax minus, which is equal to M plus X minus. If we assume an ideal solution so that the activities and equal concentrations are equal, the above reaction is cell reaction for the following cell. We can write it as M plus X minus in saturated solution, and on the other hand side we have Mx solid and metal M. The half cell reactions we can write for right hand side, that is Mx solid is taking an electron giving M and X minus, whereas on the left hand side metal is oxidizing to M plus aqueous and an electron is evolved. Overall reaction can be written as Mx solid is equal to M plus aqueous plus X minus aqueous, and E0 is equal to E0R minus E0L. Knowing the value of E0 for the cell under consideration and using the relations, we can write delta G, that is Gibbs free energy change, is equal to minus NFE0, which is equal to minus 2.303 RT log KSP, which means log KSP can be written as NFE0 divided by 2.303 RT, and E0 then becomes 2.303 RT by NF log KSP, which is equal to 0.0591 RT by NF log KSP. Thus, we can determine solubility product KSP if the value of E0 is known. Let us now come to some potentiometric titration. The potentiometric method include two types of measurement. These are direct measurement of an electrode potential from which concentration of an active ion may be found. Second, we can determine change of EMF of an electrode cell brought about by the addition of titrant. Both methods are based on quantitative measurements of EMF of the cell and is given by E cell is equal to E reference plus E indicator plus E junction. As the reference electrode potential is independent of solution and junction potential is constant, so the cell potential is a measure of indicator electrode potential and can give information on the nature and concentration of substance under test. There is a difference between a titration reaction and a cell reaction. In titration reaction, we add reactant and product in the same half cell. That is, the reactant and products, they are present in the same cell, whereas the titration reaction is always at equilibrium, whereas if we consider it with a simple cell reaction, it is not at equilibrium. Potentiometric titrations may be applied to different types of reactions. For example, an acid-base titration, oxidation reduction titrations, precipitation titrations, and complexometric titrations. So, let us now come to them one by one in a little bit more detail. Acid-base titration involves neutralization of an acid or base, and it is always accompanied by the changes in the concentration of hydrogen or OH, that is hydroxide ions. In these reactions, hydrogen electrode is used as an indicator electrode and calomel electrode is used as a reference electrode. We have already discussed hydrogen electrode and calomel electrode in detail in our earlier lectures. Now, for titration, a known volume of the acid titrant is kept in a beaker and it is continuously stirred. The hydrogen and calomel electrodes are connected by the salt bridges and connected to a potentiometer which record the change in the EMF of the solution into the beaker after the addition of base from burette. The values of EMF are then plotted against volume of titrant added and the curves are obtained. Now, at this stage, I would like to tell you that acid-base titration is different than a simple titration which you carry out in a lab using a burette and pipette. In this case, the measurements of EMF are carried out using a potentiometer, whereas in the laboratory you add an indicator and color change is monitored. The potential of a hydrogen electrode is given by an expression E is equal to E0 minus 0.0591 log activity of hydrogen ions. That is, pH is equal to minus log activity of hydrogen ions, and therefore we can write E is equal to E0 plus 0.0591 pH. As the standard electrode potential is constant, so the cell potential or EMF is proportional to the change of pH during the reaction. The point where EMF is increased rapidly is considered as the end point of the titration. A more sensitive and precise method to measure end point is to plot the slope of curve against volume, as the slope is maximum at equivalence point. The maximum value gives the end point. Now, we can plot this data in three different ways. In the first case, we can plot E cell against the volume added, and you can see we get a S-shaped curve, and the middle of the rising portion gives us the equivalent point. The second possibility is we can also plot volume against delta E of cell divided by delta V, and in this case we get a peak shaped curve, and the maximum point gives us the end point or equivalence point. If we plot V against delta square E cell divided by delta V square, in this case we get an increase followed by a decrease, and then the value comes to 0. Now, the middle point where the curve touches the 0 scale is known as equivalence point. The second type of titration comes complexometric titrations. For example, a metal electrode is used whose ions are involved in the complex formation. For example, silver electrode is used to measure cyanide ions with standard solution of silver. The reaction here is silver ions are reacting with two cyanide ions giving AgCN2, and in this case solid silver cyanide begins to get precipitated soon after the equivalence point. The further addition of silver neither changes the concentration of the complex nor changes the silver ion to any extent, so that the curve has an almost horizontal portion shortly after the equivalence point. In many complexometric reactions, the situation cannot be handled so easily because more than one complex is formed. Thus, the reaction in the case of mercuric ion with cyanide ions can be written as Hg2 plus 3 cyanide ions giving HgCN3 minus, and in the second case Hg2 plus 4 Cn minus is giving HgCN4 minus. However, these situations have become widely used because of the discovery of the metal chelating agents such as EDTA. I believe you know the full name of EDTA, which is ethylene diamine tetraacetic acid. The next type of titrations involving potentiometry are oxidation reduction titrations. Redox reactions can be followed by an inert indicator electrode. The electrode assumes a potential proportional to the logarithm of the concentration ratio of two oxidation states of the reactant or the titrant, whichever is capable of properly poisoning the substance being oxidized to substance being reduced. For example, let us consider the case of cerium ions. Here, cerium 4 plus is reacting with Fe2 plus to give cerium 3 plus plus Fe3 plus. It is generally considered that such a reaction consists essentially of two half reactions whose standard potentials may be used to calculate the standard potential of the reactions. With presence of Fe2 plus and Fe3 plus ions, the electrode behave as an oxidation reduction electrode whose potential according to the Nernst equation is given by an equation E is equal to E0 plus 0.0591 by N log oxidized by reduced. In this case, since N is equal to 1, we can write E is equal to E0 plus 0.0591 log oxidized by reduced, and E is equal to E0 plus 0.0591 log, we can write here Fe plus 3 divided by Fe plus 2, because Fe plus 3 was undergoing oxidation and Fe plus 2 was undergoing reduction. Oxidation reduction titration may be used in procedures such as monitoring of cyanide in water from metal plating industries or chlorine compounds in bleach compounds manufacturing units, and the use of these bleach compounds in paper manufacturing. They are also extensively used in water pollution, sewage treatment, agricultural and biochemical studies. Now come to the last titration, that is the precipitation titration. Any precipitation titration that involves insoluble salts of metals such as mercury, silver, lead and copper may be followed potentiometrically. The indicator electrode may be made of the metal involved in the reaction or may be an electrode whose potential is governed by the concentration of the anion being precipitated. The magnitude of the potential change at the end point depends on the solubility of the substance being precipitated as well as the concentration involved. Suppose we want to standardize a solution of silver nitrate by titrating it against a standard solution of potassium chloride. The silver electrode is used as an indicator electrode in this case. The potential of half cell silver plus silver is measured by connecting it with the calomel electrode. The solution is titrated against a standard solution of potassium chloride, the strength of which is about 10 times higher. The reaction we can write as silver ion plus nitrate ion plus potassium ions plus chloride ions is giving silver chloride plus potassium ions and nitrate ions. The potential of silver ion silver electrode is given by the Nernst equation, that is E is equal to E0 plus 0.0591 log silver ions. Let us now come to advantages of potentiometric titrations. Over classical visual indicator methods, there are many advantages of potentiometric titrations. For example, they can be used for colored, turbid or fluorescent analyte solutions. They can be used if there is no suitable indicator or the color change is difficult to ascertain, which means that if there is no suitable color change, we cannot use a common titration, rather it is easy to use a potentiometric titration. They can be used in the titration of polyproteoacids, mixture of acids, mixture of bases or mixture of halides. The apparatus required is inexpensive, reliable and readily available. It is easy to interpret the titration curve. Now, to summarize, today we have discussed applications of liquid junction potentials or concentration cells, you can say, and different types of potentiometric titrations and their applications. In this series of lectures, we have talked about different types of reversible electrodes, that is gas metalline, metal metalline and so on. Then we talked about Nernst equation, derivation of cell EMF, representation of a cell, various types of electrode, various types of standard electrodes, that is standard hydrogen electrode, reference electrode, calomel electrode and so on. Then we discussed electrolytic and galvanic cells, and then we discussed computation of a cell EMF and the thermodynamic quantities for a cell reaction. And finally, we have discussed potentiometric titrations and liquid junction potential and their applications.